Imagine you are standing in the middle of a really chaotic emergency room. The automatic doors slide open, and a frantic parent rushes in, clutching a crying infant.
Oh man, yeah. That's a high-stress situation right out of the gate.
Right, and you take one look at this child, and your heart just it drops into your stomach because the baby looks exactly as though they've suffered a terrible, full-body scalding burn.
Just incredibly red, blistering skin.
Exactly. Their skin is peeling off in these large, terrifying sheets. But, here's the medical mystery you're immediately faced with. This child hasn't been anywhere near hot water.
No heat source at all.
None. They haven't been near a fire. There's no external burn whatsoever. So what on earth is happening to this baby's skin?
It's one of the most visually alarming presentations a clinician can ever encounter, honestly.
I can only imagine. Well, the answer to that terrifying mystery is actually buried in a 2006 dermatology medical board exam from Brazil. And today, we're going to use this single, meticulously crafted exam question as our source material for this deep dive to solve the case.
It's a great mission for this deep dive because looking at this condition, it goes against your basic intuition of cause and effect,
Yeah, like you see a burn, you assume a heat source.
Right, but biology is far more devious than that. And this specific exam question is from the IP dermatology exam. It's designed to test a physician's ability to see past that initial visual shock.
To deduce the microscopic warfare actually happening inside the body.
Exactly. Even if you're not in medical school, the detective work here is completely mind-blowing.
So let's jump right into it. I have the actual exam prompt right here, and I want you, the listener, to play along with us.
Put your diagnostic hat on.
Imagine you're sitting for this board exam. The clock is ticking, your medical license is on the line. The question reads, quote, staphylococcal scalded skin syndrome. And then it provides 5 possible ways to complete that sentence.
All right, let's hear the options.
Okay, option A is caused by staphylococcal toxins. Option B is a disease where the Mikulski sign is absent. Option C exclusively has the skin as the infectious focus.
Moving right along to D&E, I assume.
Yep. Option D is most frequent in young adults. And finally, option E is exclusively affects mucous membranes.
So when you look at this question, you have to recognize what the examiner is actually fishing for here.
Which is what, exactly?
Well, they're presenting one of the most critical pediatric dermatological emergencies in existence. If a doctor misdiagnoses this, like treating it as a severe allergic reaction or something, the consequences are catastrophic.
The stakes are just incredibly high.
Yeah, very high, which is why understanding the underlying mechanism is so vital.
Well, if you guessed option A, you nailed it. The correct completion is staphylococcal scalded skin syndrome is caused by staphylococcal toxins.
But, pressing that answer reveals a pretty massive biological trap.
Right, because when you hear the word staphylococcal, your mind instantly jumps to the bacteria itself. You picture millions of microscopic bugs swarming all over the baby's skin, physically eating it away.
Which is a very logical assumption to make.
But if I were to take a cotton swab, and rub it right on that peeling skin and put it in a microscope, I'm not going to find a massive bacterial colony there, am I?
You are not, and that's the exact trap the examiners want you to avoid. To justify why option A is the only correct answer, we have to reframe how we think about infections entirely.
Okay, lay on me.
So relying on established clinical principles and guidelines from pediatric societies regarding bullous or blistering diseases, we see that this condition is fundamentally a systemic, toxin-mediated response.
Wait, I think the history books call this von Ritterstein disease, right?
Yeah, that's the historical name for it. And the key here is that the bacteria themselves might be located completely elsewhere in the body.
Wait, really? Like where?
It could be hiding in the baby's nasal cavity, in their throat, or in a tiny, seemingly insignificant localized infection.
Hold on, if the bacteria are hiding in the baby's throat, how on earth is the skin on their legs and arms peeling off?
It's crazy, right?
It is. I mean, it implies the bacteria aren't the soldiers doing the damage. They're like, the generals sitting safely behind the front lines.
That is a highly accurate way to visualize it. The bacteria are acting as a microscopic munitions factory. They set up a base camp, what we call the primary infectious focus, and they start actively manufacturing these specialized weapons.
The epidermolytic toxins.
Exactly, specifically exfoliatins A and B. These toxins seep into the surrounding tissue, they enter the local capillaries, and they're swept away by the bloodstream.
So the blood just acts as a delivery system.
Yep. It distributes them systemically to the entire surface area of the skin. The skin peeling is merely the collateral damage of a
bacteria Staphylococcus aureus is pumping out toxins that travel through the blood. Why did our ER scenario specifically feature an infant?
The demographic question. It's a really important one.
Right, because why isn't the waiting room filled with 30-year-old or teenagers with peeling skin? If the toxin gets in your blood, shouldn't it destroy anyone's skin?
You would think so, but the age specificity is actually one of the most fascinating aspects of staphylococcal scalded skin syndrome, or SSSS for short. It is predominantly a disease of newborns and children under the age of 5.
And why is that?
To understand why, you have to look at the anatomical and immunological maturity of the patient. First off, infants simply lack the specific antitoxin antibodies.
Oh, because they just haven't been exposed to enough stuff yet.
Right. As you go through life, you're constantly exposed to everyday bacteria, and your immune system slowly builds this robust library of defenses. An infant's library is virtually empty.
Okay, that makes sense.
But the second, and arguably more critical reason, comes down to kidney function.
Oh, the kidneys. I was reading about this in the sources, and it made me think of a child's kidneys as basically an under construction water filtration plant.
That's a perfect analogy.
Because an adult kidney is like a state-of-the-art facility, right?
Right. The processing power to filter these specific toxins out of the blood quickly enough.
The glomerular filtration rate. That's the key metric here.
Exactly. The glomeruli are the tiny blood vessels in the kidneys where the actual filtering happens. In a newborn, this system is operating at a fraction of the speed and efficiency of an adult's.
So the toxins just build up?
Yeah, because the kidneys can't clear the exfoliatant toxins efficiently. They just keep circulating, they accumulate in the bloodstream, eventually reaching a critical mass that triggers this catastrophic skin failure.
Wow. And that physiological reality beautifully explains why adult cases of SSS are exceedingly rare.
They are very, very rare.
So if an adult does get this, it must mean their own filtration plant has completely gone offline.
Precisely. An adult presenting with SSSS is a massive red flag for severe underlying disease. It generally only occurs in adult patients with chronic renal failure.
Because their kidneys are basically functioning like a newborn's at that point.
Exactly. If an adult's kidneys have failed, they are in the exact same physiological boat as the infant. They just cannot filter the toxins out.
Are there any other adults at risk?
The other main demographic are those with severe immunosuppression. People whose immune systems are so compromised that they can't mount any defense against the bacterial factory in the first place, allowing toxin production to reach astronomical levels.
Okay, so we have a highly susceptible patient, a newborn with an empty immune library and immature kidneys. What actually sets this whole chain reaction off?
It goes back to that hidden base camp we talked about.
Right. The sources point heavily to hidden primary infectious foci. What does a hidden focus look like in a real-world clinical setting?
Well, a focus is simply the home base for the bacteria. In newborns, one of the most common and easily overlooked hiding spots for the Staphylococcus aureus factory is the umbilical stump.
Wait, the belly button?
Yeah. The clinical term for an infection there is omphalitis. When a baby is born and the umbilical cord is cut, it leaves a small healing wound. It's essentially a direct portal into the bloodstream that is slowly closing up.
That's terrifying.
It is. And if Staphylococcus aureus colonizes that tiny stump, it doesn't necessarily manifest as a massive, visibly raging infection. It might just look like a tiny bit of redness or crusting.
So it's basically a Trojan horse.
Yeah.
The parents think it's just normal umbilical cord healing, maybe just a little irritated, but meanwhile, these microscopic factories are running double shifts inside.
Exactly. It's a localized colony, but it's enough of a foothold for the bacteria to start churning out exfoliative toxin A and exfoliative toxin B into the newborn's circulatory system.
Because the weapons we talked about.
Yes, and these two specific weapons are masterpieces of biological engineering. Staphylococcus aureus is an incredibly sophisticated pathogen.
So what is the fundamental difference between exfoliative toxin A and B? Why does the bacteria need two different weapons?
It all comes down to how the bacteria stores the blueprints for these weapons. Exfoliative toxin A is chromosome encoded.
Meaning it's in their main DNA.
Right. The genetic instructions for building it are permanently hardwired into the bacteria's core DNA. It's a stable, consistent part of the organism, and the toxin itself is heat stable, meaning it can withstand higher temperatures without breaking down.
Okay, got it. And what about toxin B?
Exfoliative toxin B, however, is plasmid encoded.
Oh, plasmids. Those are those little extra packets of DNA, right?
Yeah.
The ones bacteria can actually swap with each other like trading cards.
That's exactly what they are. Plasmids are circular, extrachromosomal DNA molecules. Bacteria can engage in a process called horizontal gene transfer.
How does that work?
They can physically connect to another bacterium using a tiny structure called pilus and just pass a copy of a plasmid across.
Man, it's essentially a microscopic arms trade.
It really is. A completely harmless strain of staph could acquire the plasmid for exfoliative toxin B from a dangerous strain and suddenly become capable of causing SSSS.
That is wild.
Now, toxin B is heat labile, meaning it degrades under high heat, but together, A and B form a devastating biological arsenal that ensures maximum damage.
All right, so we know what the toxins are, and we know they're floating freely through the infant's bloodstream because their tiny kidneys can't flush them out. But how do they actually tear the skin apart?
This is where we get into the really nitty-gritty pathophysiology.
Let's do it. What is the physical mechanism when these toxins finally arrive at the skin surface?
Well, what's truly terrifying is that these toxins are not blindly destroying tissue like an acid would. They are highly targeted precision instruments. Biochemically, they're classified as serine protease.
Okay, you're gonna have to translate serine protease into plain English for me.
Fair enough. A protease is an enzyme that breaks down proteins. A serine protease is a specific type that uses the amino acid serine as its active mechanism to cut peptide bonds.
So they're like scissors.
Yes, think of them as microscopic molecular scissors. They don't burn, they don't crush, they travel through the capillaries, arrive at the skin, and seek out one single highly specific microscopic thread to snip.
Just one specific thread. What is it?
Their exclusive target is a protein located in the epidermis called desmoglein-1 or DSG1.
Okay, DSG1. To visualize this for you listening, imagine the outer layer of your skin, the epidermis, is a sturdy brick wall. The skin cells themselves, the keratinocytes, are the bricks.
I like this analogy.
And desmoglein-1 is the mortar holding those bricks tightly together. It's what keeps your skin waterproof, tight, and resilient against friction.
Spot on.
But then these staph toxins, these serine protease molecular scissors, come floating up from the blood supply, and they specifically recognize the chemical structure of that mortar, and they just start snipping away at the desmoglein-1.
And when you cut the mortar, the wall simply collapses. In dermatological terms, this total loss of cellular cohesion is called acantholysis.
Acantholysis.
Right. The bricks are suddenly no longer attached to one another because desmoglein-1 is highly concentrated in the upper layers of the epidermis, specifically a sublayer known as the stratum granulosum or granular layer. The cleavage happens very superficially.
So it's right near the surface.
Yes. The result is the formation of incredibly fragile blisters. The topmost layers of the skin literally detach from the layers beneath them and just slide off.
It's horrifying. But wait, I have a question about this.
Go for it.
If this toxin is floating everywhere in the blood, reaching every single capillary in the body, why doesn't the inside of the baby's mouth peel away?
Yeah.
I mean, why don't the insides of their eyelids or their throat peel off? This is the most confusing part to me. If the blood goes everywhere, the scissors go everywhere. Why are the mucous membranes spared when the skin on the chest and legs is sloughing off?
You have just hit on the ultimate biological aha moment of this entire disease process. It's brilliant.
Really? How so?
It all comes back to your mortar analogy. The mucous membranes, the delicate tissues lining the mouth, the throat, the conjunctiva of the eyes, they do not primarily use desmoglein-1 to hold their cells together.
What do they use?
They evolved to use a different related type of mortar, a protein called desmoglein-3.
Wow, so the structure of the protein is different, so the scissors literally do not fit.
Exactly. The serine protease activity of the staphylococcal toxins is so highly specific, so perfectly tailored to the molecular shape of desmoglein-1 that they are completely blind to desmoglein-3.
That's incredible.
The toxins circulate through the blood vessels of the mouth, they bump into the desmoglein-3, holding the mucous membranes together, and they do absolutely nothing. They just bounce off.
Because it's the wrong molecular shape.
Right, they cannot cut it. Therefore, despite the blood being saturated with toxins, the mucous membranes remain perfectly intact and glued together. This is a crucial diagnostic clue for doctors in the ER.
That level of microscopic specificity is astounding to me. But zooming back out to the patient lying in the hospital bed, the consequences of this acantholysis are massive.
Absolutely massive.
I mean, the mortar is gone, the outer skin is peeling off. What happens to the human body when it suddenly loses its largest organ? It's not just a cosmetic issue, obviously.
No, not at all. It is an immediate multi-system crisis. The skin is your body's primary armor and its primary regulator. Without an intact epidermal barrier, the patient faces a cascading series of life-threatening events.
What's the first thing to go wrong?
The first and most pressing danger is massive fluid loss. Your skin acts as a waterproof seal, keeping your internal moisture locked in. Without the stratum corneum and the granular layer, the interstitial fluid just evaporates straight out of the underlying tissues into the air.
Oh man, like leaving a wet sponge out on the counter, it just dries out completely.
Exactly like that.
And with that water loss comes a massive disruption of electrolytes. Right.
Precisely. The sodium, potassium, and chloride balances go completely out of whack, which can trigger cardiac arrhythmias and systemic shock.
That's terrifying. What else?
The second immediate danger is severe heat loss. The skin regulates your temperature. Without that insulating layer, the infant can quickly become profoundly hyperthermic.
They just can't hold on to anybody heat.
Right. And third, ironically, is a high risk of secondary bacterial infections.
Like secondary.
Yeah. The staph toxins open the gates, they destroyed the physical barrier, and now any other random opportunistic bacteria floating around in the hospital environment can land on that raw tissue, enter the bloodstream, and cause fetal sepsis.
So the staph bacteria unlocks the door, and anything else can just walk right in.
Exactly. It's a massive vulnerability.
The sources also heavily emphasize the pain associated with this. It sounds absolutely agonizing.
It is excruciating. And the pathophysiology explains why the pain starts so early in the process. Because there is a hematogenous spread, meaning the toxins are spreading systemically through the blood, the neem endings across the entire body are irritated simultaneously.
So it hurts everywhere all at once.
Yes. Before a single blister even appears, the skin becomes diffusely red and incredibly tender to the touch. Clinicians call this the scarletiniform phase.
Scarletiniform phase. Because it looks like scarlet fever?
Exactly. The molecular scissors are actively dissolving the structural integrity of the skin, exposing these sensitive microscopic nerve endings. It makes even the lightest brush of a hospital bedsheet intolerably painful.
I can't even imagine that kind of pain for a baby. Knowing these mechanics, the immature kidneys failing to filter, the molecular scissors snipping the mortar, the catastrophic loss of fluid and temperature regulation, how does a physician actually spot this and diagnose it accurately while the clock is ticking?
It's a high-pressure situation, but the clinical presentation follows a very distinct and rapid timeline.
Okay, walk me through what the doctor sees.
It often begins with erythema, a pronounced redness that is periorificial.
Meaning around the mouth and eyes.
Right, circles the mouth and eyes, and it's also flexural, meaning it concentrates in the folds of the neck, the armpits, and the groin. Within hours, this redness generalizes into a highly painful universal exanthema, a full-body rash.
And then the blisters start?
Yes. Typically within 24 to 48 hours, the blisters form. But remember, because only the very top layer of mortar and the granular layer was cut, these are not deep, tight blisters.
They're superficial.
They are incredibly thin, flaccid, and fragile. They rupture almost immediately upon forming, leaving behind what dermatologists describe as tissue paper skin, or the raw appearance of a severe scald.
Now, there's a diagnostic term that kept popping up in the medical literature here, and honestly, it sounds like a terrifying parlor trick.
You're talking about the Nikolsky sign.
Yes, the Nikolsky sign. What exactly is this, and how does a doctor perform it?
It's arguably one of the most famous clinical signs in dermatology. It's named after the Russian dermatologist Pyotr Nikolsky, who first described it way back in the late 19th century.
Okay, so how do you test for it?
To test for it, the doctor applies light lateral rubbing pressure, usually with their thumb or maybe a pencil eraser, to an area of the patient's skin that actually looks macroscopically normal.
Wait, so not the actively blistered skin?
Right, not the blister. They test the apparently healthy, flat, red skin nearby.
Ah, I see. Because if the toxin is in the blood, the mortar is already cut everywhere, even if a blister hasn't fully formed yet.
Exactly.
Right.
The structural integrity is already gone. So when the doctor applies that light lateral fiction, the upper layers of the epidermis simply shear and slide right off the underlying tissue.
Just from rubbing it?
Yes, it just wrinkles up and creates a fresh erosion right before their eyes. The skin literally gives way under minimal pressure. If that happens, you have a positive Nikolsky sign.
Wow. That is a chilling visual, but undeniably clear for a diagnosis.
Very.
Now, speaking of diagnostics, there is a detail about the laboratory testing that feels like a complete paradox to me.
What's that?
So, if I take a syringe, extract the fluid inside one of these giant newly formed blisters, and send it down to the microbiology lab, the fluid is completely sterile.
Yes.
There is no bacteria in it. How is that possible if this is literally a bacterial disease?
This is exactly where a physician's deep understanding of the pathophysiology saves lives. Because if a doctor doesn't understand the mechanism, they'll look at a giant blister on an infant, logically assume it's a massive local skin infection, swab the blister fluid, send it for culture, and wait.
And what does the lab say?
The lab will call back 24 hours later and say no bacterial growth. The fluid is sterile.
Which could easily lead an uneducated doctor to conclude, oh, it must be a virus or an allergy, and they just stop looking for the bacteria altogether.
Exactly. And meanwhile, the hidden staph factory is just continuing to pump out toxins. We know the epidermal damage is caused by the circulating toxins, not by local bacteria eating the skin.
So the blister fluid is just, what, serum?
Yeah, the blister fluid only contains the patient's own serum and inflammatory cells. The Staphylococcus aureus is still safely hidden back at its primary focus.
The umbilical stump or the nose?
Right. To find the culprit, doctors must hunt for the factory. They need to culture the baby's nasal passages, their conjunctiva, their throat, or that seemingly minor crested umbilical stump. You culture the suspected source, never the blister.
That makes so much sense now. What about imaging? Do they rush the baby to the CT scanner or get x-rays?
Generally, imaging is useless for the skin condition itself. A radiograph isn't going to show you a canthalolysis. Imaging is only utilized if the clinical exam suggests the bacterial factory is hidden deep inside a bone.
Like causing osteomyelitis?
Right, or perhaps a deep joint infection. Otherwise, this is purely a clinical and microbiological diagnosis.
Okay, this brings us to what I think is the ultimate showdown in the ER, the differential diagnosis.
This is the critical juncture.
You have a patient with massive skin peeling. You need to know what it is immediately. The sources highlight the most life or death distinction a doctor must make, distinguishing SSSS from TEN. What is TEN?
TEN stands for toxic epidermal necrolysis. It is another devastating, life-threatening blistering condition. But unlike SSSS, TEN is usually a severe idiosyncratic hypersensitivity reaction.
A massive allergic response.
Exactly, usually to a medication such as an anticonvulsant or a specific antibiotic. Visually, at a quick glance in chaotic ER, SSS and TEN can look terrifyingly similar.
Both patients are red, they're in agony, skin is peeling.
Right, both can even exhibit a positive Nikolsky sign.
But the underlying mechanism is completely different, which means the treatment has to be totally different.
100% different.
Because if you treat a severe allergic drug reaction by pumping the patient full of more antibiotics, you might kill them.
Yeah.
And conversely, if you treat a bacterial infection with heavy allergy medications that suppress the immune system, the bacteria will just multiply out of control. This is the razor's edge of clinical medicine. This is where we apply what the sources call expanded clinical judgment.
Sounds intense.
It's basically a multi-layered diagnostic breakdown that functions like a detective's checklist to separate SSSS from TEN. Let's look at the layers. First, the etiological layer. What is the root cause?
So for SSSS, it's a systemic infection by Staphylococcus aureus, and for TEN, it's an immune reaction to a drug.
Exactly. Second, the syndromic layer. What is the broad category of what is happening? In SSS, it is a toxin-mediated acute epidermal detachment.
And the third layer is the clinical layer. This seems to be the holy grail of the physical exam. The sources mention a diagnostic triad for SSSS.
Yep, the triad is key.
You were looking for a fever, a positive Nikolsky sign, and this is the callback to the mucosa mystery we discussed earlier, spared mucous membranes in a pediatric patient.
Yes, because TEN, the allergic drug reaction, does not care about the difference between desmoglein 1 and desmoglein 3.
It just destroys everything. The massive immune response in TEN attacks the epithelium indiscriminately. It destroys the mucous membranes violently.
So, if the baby's lips are bloody and crusty, if the inside of their mouth is raw and blistering, and their eyes are severely inflamed with sloughing tissue, you are likely looking at TEN.
Correct.
But if their mouth looks completely pink, healthy, and untouched while the skin on their chest is peeling away, you are looking at SSSS.
Precisely. That subtle biological difference in the protein mortar becomes the defining clinical clue.
That's amazing.
Moving down the checklist, the fourth layer is topographical. The SSSS rash is generalized, but noticeably starts and concentrates in the anatomical folds, the neck, armpits, and groin.
And the final layer.
The definitive layer. If the clinical picture is still murky, the doctor will take a tiny, rapid, frozen section biopsy of the peeling skin and look at it under a microscope.
What does the microscope reveal?
In SSS, the biopsy will show a very shallow subcorneal cleft. This means the split in the skin layers is right at the very top surface, in the granular layer.
Because that's exactly where the desmoglein 1 mortar was concentrated and cut.
Right. In TEN, however, the cell death is much more profound. The microscopic split occurs much deeper, right at the dermo-epidermal junction, where the entire epidermis meets the deeper dermis.
So the SSSS peel is shallow, the TEN peel is deep.
Exactly. That's the definitive proof.
Okay, so the diagnosis is locked in, the detective work is done, and it is officially SSSS.
Yeah.
But the baby is still losing fluid, losing heat, and in agony. How do we treat this? We have to shut down the factory, right?
The immediate non-negotiable goal is eradication therapy. We must stop the production of new toxins. This requires administering immediate intravenous antibiotics.
But you can't use just any basic antibiotic, can you?
No, you can't. Staphylococcus aureus is a notoriously resilient and adaptable organism. Most strains produce an enzyme called penicillinase.
What does that do?
It essentially acts as a chemical shield that actively destroys basic penicillin by breaking its beta-lactam ring.
It's literally a bacteria that brings its own anti-missile defense system.
Exactly. So you must bypass that defense by using penicillinase-resistant antibiotics, such as oxacillin or nafcillin.
What if the local hospital has a lot of MRSA, methicillin-resistant Staphylococcus aureus?
That's a highly mutated strain that resists even those drugs. If MRSA is suspected or prevalent, you cannot waste time. You immediately escalate to vancomycin or linezolid. You have to nuke the bacterial source site to permanently halt the assembly line, producing exfoliative toxins A and B.
Okay, so shutting down the factory stops new toxins from entering the blood, but what about the baby right now? They're missing a huge percentage of their protective barrier. We talked about massive fluid evaporation.
That requires massive, meticulous physiological support. The patient is treated in a manner nearly identical to a severe burn victim.
Even though there's no actual burn.
Right. Because they are losing so much interstitial fluid through evaporation, we must provide vigorous, aggressive intravenous hydration and precise electrolyte replacement to prevent cardiovascular collapse.
And temperature control.
They need strict temperature regulation in incubators or heated rooms to prevent hypothermia. They also require aggressive pain management, usually intravenous opioids, because the exposed nerve endings are agonizing.
What do you actually put on the skin? Do you wrap them in thick bandages?
Actually, the local wound care must be incredibly gentle. You want to avoid any mechanical trauma that would induce further Nikolsky shearing.
Oh, because just rubbing the bandages could peel more skin off.
Exactly. Clinicians use sterile saline compresses, liberal application of bland emollients like petroleum jelly to create an artificial moisture barrier, and non-adherent dressings. You never use tight, sticky tape or harsh topical antiseptics that would further damage the delicate, newly forming cells.
So here's a major question I had regarding the treatment protocol when I was reading through this.
Sure, what is it?
If the skin is so incredibly inflamed, red, and angry due to this massive immune and inflammatory response, shouldn't we give the patient a heavy systemic dose of corticosteroids? Corticosteroids are fantastic at calming down severe inflammation, right?
Yeah.
Why not use them to shut off the immune system's overreaction?
This raises one of the most important life-saving physiological points of the entire deep dive. And it actually connects directly to the Nobel Prize-winning science we will discuss a bit later.
Okay.
The answer is absolutely not. Corticosteroids are strictly, universally contraindicated in staphylococcal scalded skin syndrome.
Why? I mean, if it reduces the redness and inflammation, wouldn't that help the baby feel better?
To understand why it's fatal, we have to look at what corticosteroids actually do at a cellular level and connect it to the work of Bruce Buehler, who won the 2011 Nobel Prize for his discoveries regarding innate immunity.
Okay, what did he discover?
Buehler discovered toll-like receptors. These are basically the microscopic sentinels on our cells that detect bacterial invaders. When these sentinels detect the massive flood of staphylococcal superantigens, they sound a systemic fire alarm.
And that alarm causes the inflammation.
Exactly. This alarm causes the massive inflammation, the fever, and the recruitment of white blood cells to fight the infection.
So the inflammation is the body's military mobilizing for war.
Precisely. The root cause of this disease is a live, actively multiplying, toxin-producing bacterial infection. If you administer systemic corticosteroids to this baby, you are artificially silencing that fire alarm.
You're turning off their immune system.
You are chemically suppressing their immune system. You are essentially telling their white blood cells to stand down and go to sleep. And while the immune system is medically paralyzed, the Staphylococcus aureus bacteria are free to multiply exponentially, build hundreds of new factories, and pump out lethal amounts of toxin.
Wow.
Giving steroids turns a localized bacterial factory into an unhindered, overwhelming, and rapidly fatal sepsis.
That makes perfect sense. You cannot disarm the military while the enemy is still building weapons in the background. So definitely no steroids.
Never.
Assuming the correct antibiotics and hydration are given, what is the prognosis? Does the skin grow back normally?
Surprisingly, the prognosis is excellent, and it is a direct result of the specific pathophysiology we discussed.
Because it's so superficial.
Exactly.
Yeah.
Because the molecular scissors only target desmoglein 1 in the granular layer, meaning the cleavage is exceedingly superficial, the basal layer of the epidermis, and the entire dermis beneath it remain completely unharmed.
So the base layers are still intact.
Right. The stem cells responsible for regenerating the skin are perfectly fine. Therefore, the re-epithelialization process is remarkably fast. The skin usually heals completely within 5 to 7 days.
That's incredibly fast. And what about scarring? It looks so traumatic, you assume the child would be scarred for life.
Amazingly, because the deeper dermal layers where scar tissue forms were never breached, it heals without leaving any scars whatsoever. It is essentially like an incredibly aggressive, natural, full-body chemical peel. With prompt and appropriate treatment, the mortality rate in children is very low, typically less than 5%.
But for adults, the story is entirely different, isn't it?
Tragically, yes. In those rare adult cases we mentioned earlier, the mortality rate skyrockets to over 60%.
Over 60%. Why so high?
We have to contextualize that statistic. The staphylococcal toxin is not necessarily more lethal to adult skin. Rather, the high mortality is a reflection of the adult's underlying health.
Right. The adult cases only happen if their kidneys are already failing.
Exactly. For an adult to develop SSS in the first place, their system must be profoundly broken. They must already be suffering from end-stage renal failure, severe immunodeficiency, or advanced malignancies.
So they're already on the brink.
Their bodies are already pushed to the absolute limit, and they simply lack the physiological reserve to survive the additional massive cardiovascular and infectious trauma of losing their entire skin barrier.
That's incredibly sad. Let's loop back to the board exam question that sparked this entire investigation to ensure we have a flawless grasp of the concepts.
Let's do it.
We know option A was correct. It is caused by toxins. But let's demolish the incorrect alternatives based on the physiological mechanisms we've learned today. Why is option B, which claimed the Nikolsky sign is absent, incorrect?
Well, the Nikolsky sign is the hallmark physical exam finding of this condition. Because the systemic toxins have cleaved the desmoglein 1 mortar throughout the entire superficial epidermis, applying lateral pressure inevitably causes the skin to shear off.
It's always positive.
Always. Therefore, claiming it is absent demonstrates a fundamental misunderstanding of the acantholytic process.
Makes sense. Now, option C claimed that SSS exclusively has the skin as the infectious focus.
We systematically disprove this by highlighting the extracutaneous nature of the primary infection. The bacterial factory is usually hiding in the spharynx, the umbilicus, or the conjunctiva.
So the skin is just the victim, not the source.
The skin is merely the distant victim of the circulating toxins, not necessarily the site of the bacterial colony itself.
Right. Now, option D claimed it is most frequent in young adults.
Completely false due to the maturity of the adult renal system. The fully functioning glomeruli in healthy young adults filter the exfoliatants out of the blood before they can accumulate.
So it's a pediatric disease.
Overwhelmingly. It specifically targets children under 5 whose immature kidneys cannot clear the toxins efficiently.
And finally, option E claimed it exclusively affects mucous membranes.
This is the exact opposite of reality and represents a total failure to understand the molecular target. This is our mucosa mystery solved.
Because of the different mortar.
Right, because mucous membranes rely on desmoglein 3 for their cellular adhesion, and the exfoliatant toxins can only cut desmoglein 1. The mucous membranes are completely blind to the toxin.
They're uniquely spared.
They are specifically and universally spared in SSS, which, as we discussed, is the primary way we differentiate it from 10.
It is incredibly satisfying to understand not just what the right answer is, but the precise cellular mechanisms of why the wrong answers are incorrect.
It's how you truly master the material.
To truly cement this pathophysiology in our minds, let's step outside the human hospital for a moment. Biological mechanisms rarely exist in isolation. How do these themes of barrier failure, microclimates, and targeted toxins appear elsewhere?
Comparative biology is a great tool here. To start, let's analyze the anatomotopographic behavior of the disease on the human body itself.
What do you mean by anatomotopographic?
Basically, where the lesions actually form on the body and why. Why does this profound redness and initial blistering so frequently begin its visible rampage in the anatomical folds, the axillae or armpits, and the groin?
Because it's not a random distribution, right?
It's not random at all. These intertriginous areas, the folds, naturally possess higher humidity, higher temperatures, and increased friction. This creates a perfect, localized microclimate that strongly facilitates bacterial proliferation.
Oh, it's basically a greenhouse for bacteria.
Exactly. If the initial staphylococcal factory is located nearby, or if the toxins are accumulating systemically, the combination of a high moisture environment and constant skin-on-skin friction will cause the weakened epidermis in these folds to fail and slough off first.
Okay, but what about the opposite extreme? The thick, callous skin on our hands and feet. How does SSS affect the palms and soles?
That presents a fascinating anatomical variation. The palms and the soles possess a uniquely dense, thick outer layer called the stratum corneum, which is heavily keratinized to withstand walking and grasping.
Right, because we use them constantly.
Because this layer is so incredibly thick, it acts as a robust physical shield. Now, the toxin is still in the blood supply there, and it is still cutting the desmoglein 1 mortar beneath that thick layer.
But the skin doesn't peel off.
Not right away. The sheer mechanical weight and density of the stratum corneum physically hold the dead skin in place much longer. Consequently, the characteristic blistering and the Nikolsky sign might be significantly delayed or much harder to elicit in these specific areas compared to the thin, delicate skin on the eyelids or the belly.
That makes perfect sense mechanically.
And finally, from a topographical perspective, it is crucial to remember that SSS does not follow dermatomes.
Dermatomes being the nerve pathways.
Right. It does not track unilaterally along specific nerve pathways the way shingles does. Because it is a blood-borne systemic toxin, it is universally distributed. It goes everywhere the blood goes.
Okay, now for the animal analogies drawn from the sources, I find this comparative biology absolutely fascinating. Let's start with the amphibian class. How does a frog relate to a baby with SSS?
Amphibians, such as frogs, toads, and salamanders, are profoundly reliant on their highly permeable skin barrier. For them, the skin is not merely armor, it is a critical organ for maintaining internal moisture and, crucially, for cutaneous respiration.
So they physically breathe and exchange gases through their skin?
Yes, they do. If you compromise an amphibian skin, perhaps by exposing it to a harsh environmental chemical or a fungal pathogen like chytrid, the animal fundamentally loses its ability to maintain its internal osmotic balance.
So they dry out.
It will rapidly succumb to catastrophic dehydration and suffocation. This physiological crisis perfectly mirrors the most immediate life-threatening danger to an infant with SSS.
The massive uncontrolled fluid evaporation due to sudden epidermal barrier failure.
Exactly. It's the same core vulnerability.
The next animal connection is a bit more menacing, I have to say. The brown spider, specifically those within the Loxosceles genus. I know spider venom causes flesh to rot, but how does its mechanism relate to our staph bacteria?
It is a brilliant lesson in comparative biochemical warfare. Both the venom of the brown spider and the exfoliative toxins of Staphylococcus aureus utilize destructive proteins to inflict massive tissue damage, but their specific targets and resulting macroscopic damage are vastly different.
How so?
The brown spider's venom contains a potent enzyme called sphingomyelinase D. This enzyme specifically attacks and cleaves the head off lipid molecules within cell membranes and the endothelial lining of blood vessels.
It attacks the blood vessels themselves.
Yes, this destruction causes severe vascular necrosis or vasculitis, followed by profound local tissue death and a massive, unregulated inflammatory cascade. The venom literally rots the tissue by aggressively cutting off the local blood supply.
Yikes.
It results in a deep, black, necrotic ulcer that takes months to heal and leaves severe scarring.
So it's a necrotic ulcer versus a superficial peel.
Exactly. The staphylococcal bacteria, as we've exhaustively detailed, uses its serine protease toxins to specifically target cellular adhesion proteins, the desmoglein mortar, high up in the epidermis. It does not destroy the blood vessels, and it does not kill the deeper dermal tissue.
Right. One causes deep, rotting necrosis. The other causes a clean, superficial, acantholytic peeling.
Both are devastating biological toxins, but they utilize entirely different microscopic mechanisms, resulting in vastly different clinical outcomes.
And the final animal analogy is incredibly visually evocative. The crab, specifically from the Amphora brachiura.
This is a great one. Crabs and many other arthropods must periodically shed their hard, restrictive outer exoskeleton in order to grow. This biological process is known as molting, or exedesis.
Right. It's totally normal for them.
It is a natural, highly regulated, and essential physiological event. When a crab prepares to molt, it begins separating its old shell from the underlying epidermis, but crucially, it has already synthesized a soft, new, protective shell underneath, ready to harden the moment the old shell is discarded.
It's got a backup plan.
We can conceptualize SSS as an acute pathological molt of the human epidermis. The infant is suddenly shedding their entire outer layer, peeling away their casing, much like a crab.
But tragically, because this is an uncoordinated, toxin-mediated disaster and not a natural growth process, the human patient does not have a new, fully formed protective layer waiting underneath.
No, they don't. They are left raw, completely exposed, and vulnerable to the elements.
That is a heartbreaking but incredibly effective way to conceptualize the danger. Now, reaching this level of understanding, knowing about serine proteases, cutting specific adhesion proteins, understanding the intricacies of the immune system's fire alarms, this knowledge wasn't just handed to humanity.
Oh, not at all. It was hard won.
It took world-class, paradigm-shifting scientific breakthroughs over the last century. Let's look at the giants whose shoulders we are standing on to understand this disease.
To truly appreciate how we diagnose, comprehend, and treat SSS today, we can draw direct theoretical lines to the groundbreaking work of 3 distinct Nobel laureates.
Who's the first?
Let's begin with the foundational concept of the disease itself, identifying the bacterial culprit. In 1905, the German physician and microbiologist Robert Koch was awarded the Nobel Prize in Physiology or Medicine.
Before Koch, the medical understanding of disease was incredibly primitive, right? The prevailing idea was the miasma theory that sickness was caused by bad smells, night air, or imbalances in bodily humors.
Precisely. If a baby was peeling, a 19th century doctor might blame damp air or a cursed environment. Koch shattered that paradigm. He formulated his famous Koch's postulates.
What are those?
There were a rigorous set of scientific criteria that finally allowed medicine to transition from superstition to hard, reproducible science. He definitively proved that specific microscopic organisms cause specific macroscopic diseases.
So he proved bacteria cause disease.
By isolating and identifying bacteria, his foundational work allowed subsequent researchers to identify Staphylococcus aureus as the actual physical agent responsible for these infections.
It shifted everything.
It shifted the entire global paradigm of medical treatment toward targeted antimicrobials instead of just opening a window to air out the miasma. We could not formulate the concept of shutting down the factory with antibiotics if Koch hadn't taught us how to prove the factory existed.
That is the literal foundation of modern infectious disease. Amazing. The second laureate connects back to the massive fluid loss we discussed, the amphibian analogy. Peter Agre, who was awarded the Nobel Prize in Chemistry in 2003. What did he discover?
For decades, scientists knew that water moved rapidly in and out of cells far faster than simple diffusion across a lipid membrane could account for. They theorized there must be some kind of plumbing system, but nobody could find it.
So what did Agre find?
Peter Agre discovered aquaporins. These are highly specialized, dedicated protein channels embedded within our cell membranes that selectively conduct water molecules in and out of the cell while preventing the passage of ions and other solutes.
They are literally the microscopic plumbing pipes of the human body.
Yes. When a patient with SSS loses their outer skin barrier, they experience massive, life-threatening fluid loss through the exposed underlying tissues. We can now understand and attempt to manage this profound physiological crisis at a granular molecular level because Agre's pioneering work illuminated exactly how water fundamentally moves through human tissues.
And the third laureate, whom we touched on earlier during our discussion on the dangers of corticosteroids, is Bruce Butler. He won the Nobel Prize in 2011 for his discoveries concerning the activation of innate immunity.
Yes, Butler's work revolutionized our understanding of how the body's initial defense system detects an infection and raises the alarm. He discovered the receptor proteins, specifically toll-like receptors that recognize molecular patterns on bacteria and other pathogens.
The sentinels.
Right. When the staphylococcal toxins, which act as superantigens, flood the infant's bloodstream, the host's immune system does not just sit there passively. The toll-like receptors bind to these foreign molecules and trigger an explosive systemic inflammatory response cascade.
The fire alarm.
Butler's research provides the intricate biological circuitry that explains the massive fever, the severe localized redness of the scarletiniform phase, and the acute systemic inflammation that accompanies the skin peeling. He mapped the exact molecular wiring of the body's fire alarm system.
Which is precisely what corticosteroids dangerously attempt to shut off.
Exactly.
It truly puts it all into perspective. A single suffering infant in a chaotic emergency room is actually the focal point for over a century of Nobel Prize-winning scientific discovery.
It's all connected.
We have covered an immense amount of ground today. Let's synthesize everything we've learned and close this case file. If we are the medical detectives reviewing the final report on this disease, what are the definitive clues and management strategies that save a life?
Synthesizing this entire investigation, staphylococcal scalded skin syndrome is a critical pediatric dermatological emergency characterized by acute epidermal detachment.
Say that 10 times fast.
Right. It is caused by circulating staphylococcal toxins, specifically the serine proteases exfoliatin A and B, that travel from a remote, often hidden primary infection site to the skin. There, they highly specifically cleave the desmoglein 1 adhesion proteins in the superficial granular layer.
And the management.
Management mandates immediate intensive clinical support to counteract massive fluid and temperature loss, coupled with targeted penicillinase-resistant antibiotics to permanently eradicate the remote bacterial factory.
Let's clearly define the differential markers that distinguish this from other blistering diseases for the final time.
The defining features are the overwhelming prevalence in children under 5 due to immature renal clearance, a uniformly positive Nikolsky sign where normal-appearing skin easily shears off under lateral pressure, and crucially, the absolute sparing of the mucous membranes because they utilize desmoglein 3, which the toxins cannot cut.
And these features reliably distinguish SSS from the deep, drug-induced mucosa-destroying blistering seen in tan.
Yes, they do.
To help lock this clinical picture into memory, the sources provided a fantastic linguistic trick utilized by Brazilian medical students. It is an acronym based on the Portuguese word for skin, which is PELE. Let's break that down.
It's a brilliant mnemonic device. The P stands for pupa mucosus, which translates to spares mucosa.
Okay, P is for sparing the mucosa.
The E stands for exfoliatina, directly reminding the clinician of the exfoliatant toxin responsible for the cleavage. The L stands for limpa, which means clean, reminding the doctor that the fluid inside the superficial blisters is completely clean or sterile, containing no bacteria.
Right, the sterile fluid.
And the final E stands for escaldada, which directly translates to the scalded, burned appearance of the sloughing skin, PEL. It perfectly encapsulates the disease.
That is incredibly useful. And there's one more fascinating linguistic quirk from Brazil regarding the Nikolsky sign. In colloquial Portuguese, there is a verb niscar, which translates to peel or to flake off easily.
That's clever.
Yeah, so students are taught that if the skin niscars under pressure, the Nikolsky sign is positive. It is a perfect phonetic match for a critical clinical sign.
That's a great study hack. Now, before we conclude, there is one final illuminating connection that ties this massive systemic disease back to a very common pediatric ailment.
Here is it.
We're all familiar with standard bullous impetigo, the localized crust nasty, honey-colored blisters children frequently get on their faces or limbs.
Yeah, impetigo is super common.
Well, the pathophysiological reality is that bullous impetigo and staphylococcal scalded skin syndrome are fundamentally the exact same disease process, simply occurring on vastly different scales.
Wait, really? Impetigo is just a mini version of this?
Exactly. Standard bullous impetigo is caused by the exact same strains of Staphylococcus aureus, producing the exact same exfoliating toxins, cutting the exact same desmoglein 1 proteins.
So why doesn't impetigo cause all your skin to fall off?
The monumental difference is the capability of the patient's immune system. In impetigo, the patient's local immune response and mature renal clearance successfully manage to contain the toxin right at the site of the bacterial colony.
So it's contained.
The cleavage happens, but it remains localized to a single blister. SSS is simply the catastrophic result of what happens when the infant's body fails to contain the threat. The localized skirmish breaks containment, the toxin goes systemic into the bloodstream, and the local blister evolves into a full-body, life-threatening event.
A localized border skirmish versus a full-blown systemic war. That is an incredible way to conceptualize it. Well, that brings us to the end of today's deep and intensive medical investigation. We have journeyed from a frantic ER down to the molecular scissors cutting microscopic mortar in the epidermis and through the halls of Nobel history.
All driven by the desire to answer a single dermatology board exam question.
It truly highlights the profound interconnectedness of human biology, demonstrating how a microscopic alteration in a single protein bond can manifest as a massive, systemic, and visually terrifying clinical crisis.
It's a humbling topic.
It really is. But before we officially sign off, I want to leave you with one final, deeply provocative thought drawn from the epidemiological data in our sources. We've spent this entire time conceptualizing Staphylococcus aureus as this terrifying alien bacterial factory invading the body to pump out flesh-destroying toxins.
Right.
But here's the stark reality. Staphylococcus aureus lives naturally right now on the skin and inside the nasal passages of roughly 30% of the completely healthy human population at any given moment.
Everywhere.
It is a normal, everyday resident of the human microbiome. So if this potentially lethal toxin-producing organism is already living peacefully on your skin or in the noses of the people sitting around you right now, what are the invisible microscopic environmental triggers or the tiny genetic flips that silently dictate whether it remains a peaceful, unnoticed passenger or suddenly shares a plasmid, transforms into a deadly munitions factory, and begins melting the skin off its host?
That delicate, invisible balance between symbiosis and pathology is a question that continues to drive the forefront of microbiological research today.
Something to ponder deeply the next time you casually touch your face. Thank you for listening. Keep questioning the complex biological world around you, and always remember, things are rarely as simple as they appear on the surface, even when it looks exactly like a scalding burn. We will see you next time.